Okay. In the last class, we were trying to see the requirement of a filter because of the problems of harmonics. So, we will study a very simple design of what is known as a single tuned filter. So, as the name suggests, single tuned filter is designed for minimizing one particular harmonic frequency. So, single means one frequency. So, it is tuned for one harmonic frequency. So, it is a series combination of a capacitance, inductance and resistance CLR. So, we saw that there are some situations where the values of L and C chosen may not meet the requirement. So, that is actually quantified by defining a quantity called delta. So, the original definition of delta is omega h minus omega ho divided by omega ho. So, omega h is the actual angular frequency, sorry, omega h is the angular frequency, omega ho by definition is 1 by root LC. So, let me rewrite that particular equation. So, I will not go through all the steps. The last equation that we got was GF squared plus BF plus square root of C by L 1 by 4 delta whole square is equal to root C by L 1 by 4 delta whole square. So, for a given value of delta, this appears to be, this is actually an equation of a circle in the complex plane with the, on the real axis I have GF, on the imaginary axis I have BF. Okay. Now, if you look at delta, delta actually lies in a range. Delta min is the lower limit and delta max is the upper limit. Okay. So, delta is within a certain range. Suppose I take delta max is greater than 0. Now, if I try to plot the curve given by this equation in this plane where I have on one axis GF and the other axis is BF. Now, when it comes to showing the graph of this equation, so for what I will do is I will try to take delta equal to delta max. See, there are two extreme values of delta min and delta, two extreme values of delta min and delta max. These are the worst case values. So, I will take the one on the higher side, delta max. So, if delta is equal to delta max, which is greater than 0, then this is an equation of a circle. Okay. But one thing to note is, okay, let me take the circle. So, the center of the circle is minus root C by L 1 by 4 delta. Okay. So, it lies on the BF axis and the radius is root C by L 1 by 4 delta. Okay. So, it appears as if the circle is in the third quadrant and fourth quadrant, but GF is positive. So, GF is positive, to be more precise, GF is non-negative. GF is non-negative. Okay. So, what I can do is, I can just show the relevant part of the circle, which is just a semicircle. So, if I take this length, so this length is the diameter of the circle. So, the diameter of the circle, please note I am trying to consider one particular value of delta, which is delta max. So, this is 1 by 2 delta max under root c by L. So, this is the diameter. Radius is root c by L 1 by 4 delta max. So, the center of the circle is somewhere here. So, center is 0, the value of GF is 0 there at the center, and the value of BF is minus root c by L 1 by 4 delta max. So, C and L are positive, they are taking the positive square root, and there is a minus sign, and delta max is positive. So, the filter admittance at the harmonic frequency should lie at some point on the semicircle, that is the point. Okay. So, we have to design the filter. So, we do not have the exact value of GF or BF, that is how is designed. So, getting the value of R, L and C, or in other words getting value of GF and BF is design. Okay. Now, for the sake of filter design, what we will do is we will consider an equivalent circuit. So, let us do the design of single tune filter. So, the model considered here is, for the converter we just take the harmonic frequency which has to be minimized. So, the harmonic is in the current. So, the converter is represented by a current source, I mean it has a current source IH. Then there is a filter which is represented by an admittance, and there is a network, the external network. See, this network is the network on the AC side. Okay. So, I have converter here represented by a current source. I have between the network and the converter there is a filter represented by an admittance, and this is the network. So, let the admittance of the filter, so we have already given a notation for this. The admittance of the filter at the harmonic frequency for which it is designed is YFH, and let the admittance of the network YN, N for network, and since it is at the harmonic frequency YNH. So, the current that actually flows through the filter has a magnitude, say IFH, and the voltage across the converter or filter or network at the harmonic frequency has a magnitude, say VH. By magnitude I mean the RMS value. Okay. Now, when we want to design something, of course we try to take some parameters and try to minimize or maximize a few quantities, say that is what is all about design. Of course, one of the parameters, one of the quantities that we minimize is of course cost. Say, when it comes to design, the two things that matter are performance and cost. So, we need to somehow have good performance, at the same time we want least cost which will get that performance. Okay. Now, when it comes to performance, the objective is to minimize. See, please note the converter has a harmonic current source IH. So, due to the converter there is a harmonic current. Now, if that should not affect the network, then it means VH is the effect of IH. See, if IH is not there, only fundamental is there, then VH is 0. See, VH means it is the RMS voltage at the harmonic frequency. So, if only fundamental is there, VH is 0. So, essentially we want to minimize VH. The objective is to minimize VH. So, what is VH? So, if I look at the expression for VH, I can write VH as the converter current IH divided by the admittance of the parallel combination of filter and network. See, VH is the voltage across network or filter or converter. So, I can write this as IH divided by the magnitude of Y of H plus Y N H. See, when I have two admittance in parallel, the effective admittance is sum of the admittances. Okay, the magnitude of the effective admittance into the magnitude of the current gives the into magnitude of the voltage gives the magnitude of current. Okay, so now let us see how this YNH takes values. So, network admittance. So, when I take network admittance, that is YNH. So, again I take the complex plane. So, the complex plane the real part is the conductance of the network admittance and the imaginary part is the susceptance. Okay. Now, the question is, where will this network admittance lie? Which quadrant or which quadrants? It is possible to have values in all the 4 quadrants. First and second, first and fourth, because conductance is positive. Okay. Now, susceptance can be positive or negative. Now, why? Yeah, if it is only inductive, then where it will lie? Fourth. But the network consists of transmission line, transformers. If you take transmission line, it is not just inductive, there is a shunt conductance also. So, there is a shunt capacitance as well. So, whenever there is a capacitance, there is a possibility of positive susceptance. So, it can lie in the first quadrant and the fourth quadrant. So, it does not lie in the entire first or fourth quadrant. It can be shown that this lies in this sector. So, there are two straight lines passing through the origin. So, if I take the intersection of the areas to the right of these two straight lines, then the network admittance will lie in this area. Okay. So, this angle is called phi m. Similarly, the angle here is also phi m. So, the two straight lines make an angle of phi m with respect to the conductance axis. So, it is an infinite region. So, essentially the network admittance is having having an angle which is between minus phi m and plus phi m. So, network admittance or in fact impedance, both have the same phase angle, say both have the same phase angle range. Okay. One is the reciprocal of the other. So, network admittance angle is between minus phi m and plus phi m. So, we just saw that the objective is to minimize VH as far as the performance is concerned. Now, when we try to minimize VH, please note what is under the control of the designer. So, when I say design of single tune filter, the only values which the designer will decide are L, C and R, nothing more than that. Okay. When it comes to network, the designer has no control over the network. Designer has, of course, has no control over IH. IH is known. We know what is the harmonic current in the converter. Okay. So, when it comes to the quantities which are not under the control of the designer, but they are not fixed as well, they keep varying, then one has to choose a value. many a times we can't just take the range as it is for some of the quantities, we have to take one particular value. Okay. So, if that quantity which is not under the control of the designer is within a range, which value do you take?
The one which corresponds to the most usual case.
Okay, that is one possible answer. Do you do that? Is it when it design, we always design for worst case. So, when it comes to maximizing performance, you want to see that it performs very well even in the worst case. Okay. So, worst case is something which is chosen if you have the performance in mind. So, right now I am talking about performance. Okay. So, objective is to minimize VH, means it somehow maximizing performance. So, we take the worst case for all the quantities which are not under the control of the designer, but which vary over a certain range. Okay. So, the quantities not under the control of the designer. Designer means just filter designer. So, we are not doing any other design, only filter design. Filter designer are chosen pessimistically. That means we are choosing the worst case, pessimistic. So, that means to maximize VH. So, say our objective is to minimize VH. Pessimistically means, okay, I will remove the comma here, to maximize VH. So, maximizing VH is actually equivalent to minimizing the denominator in the expression for VH, for a given IH is constant. Okay. So, here what I am trying to say is YNH, I have not given the value of YNH. YNH I have just said it lies somewhere in the first quadrant or fourth quadrant. I have shown the region also. So, which value to be taken in order to design. Okay. So, to maximize VH or minimize the absolute value of YFH plus YNH. So, if I want to do this, so let us say how to minimize this, how to minimize the absolute value of YFH plus YNH. Now, what I will do is, we will try to take the worst case of YNH, but YFH is yet to be designed. Now, suppose I take the worst case for YNH for a given value of, say, please note we have not yet decided YFH. So, for a given YFH, I will take this next page. So, GF, this is BF. So, I have this semicircle. So, YFH is given, that means this YFH first of all should lie on this semicircle. So, it is somewhere on the semicircle, we do not know where it is. So, let us assume that some value is given. So, if YFH is given, suppose this is YFH, okay. This is YFH. Please note GF and BF are real and imaginary parts of YFH. Now, to this I have to add YNH. Now, what I will do is I will just take this region. See, the network admittance is lying in the first or fourth quadrant. So, I will take the origin of this network admittance and shift it to this point YFH. So, that is essentially saying that so to YFH I am adding YNH. suppose y and h, I have to take between these two dashed line which makes an angle phi m and another dashed line which makes an angle minus phi m. Suppose I take y and h to be this. Okay. Then y of h plus y and h. Okay. So, okay, I will try to use different colors so that it will not cause confusion. So, this blue complex number is y of h plus y n h. So, my intention is for a given y of h, I should minimize y of h plus y n h magnitude of y of h plus y n h. So, is it clear that y n h should be on the boundary? See, the boundary is this dashed line and it should be on the boundary which makes an angle phi m with respect to the conductance axis, not the minus phi m. See, what I am trying to say is it clear that it should lie on this boundary? Okay. But where, at which point on this boundary? This is, I mean, school geometry. I have to take a point on this line which is having the shortest distance from the origin. Is it? Drop a perpendicular. See, I have a point, I have a straight line. I want the point on the straight line which is having the minimum distance with from the given point. So, I have to drop a perpendicular from that point to the straight line, that is all. Okay. So, it is essentially like this. Okay, let me redraw. So, suppose this is y of h. Now, in order to find the least magnitude of, in order to find y n h such that it results in least magnitude of y of h plus y n h, what I should do is first drop a perpendicular from the origin to the boundary which makes an angle phi m. Okay. So, the boundary is this which makes an angle phi m. So, that should give the least value of the magnitude of y of h plus y n h. Okay. Yes. If y n h is 0, then it results in least magnitude of y of h plus y n h. See, we are adding two complex numbers, y of h and y n h. So, we want to minimize the absolute value of this sum of the two complex numbers. So, if y of h itself, say it is possible that I can have the sum of these two complex numbers smaller in magnitude compared to the just the magnitude of y of h. Okay. So, I can choose y and h in order to get a value which is smaller than y of h. So, if this is y of h, blue complex number is y of h plus y n h and the red one is y of h. So, that means the difference between these two is y n h. So, if I take this is y n h. So, here this sum of y of h and y n h is perpendicular to this boundary which makes an angle phi. Okay. Fine. Okay. Now, please note what we have done here is chosen the value of y n h pessimistically, that is the worst case value. Now, how to choose y of h? Now, y of h is under the control of the designer. How to choose y of h? How to choose y of h? Yeah, as far as the performance is concerned, I want to maximize the performance, that is minimize the value of VH, or it is essentially saying maximize the value of the denominator in the expression for VH. So, how to choose y of h? See, in the previous case, for some arbitrary value of y of h, we know how to choose y n h. Now, how to choose y of h itself? I do not think I am asking a very tough question. See, y n h is not under the control, we take worst case. Y of h is under the control of the designer, so we take the best case. So, how to get the best case? Worst case means the one that minimizes the absolute value of y of h plus y n h. So, the best case is the one that maximizes the absolute value of y of h plus y n h. So, y of h should be chosen to maximize y of h plus y n h absolute value. Now, how should one choose y of h? So, please note in the last figure that I got, y of h was taken to be some arbitrary value. Now, the question is how to take this. So, how to find y of h which actually maximizes the absolute value of y of h plus y n h? See, the same rule holds as far as y n h is concerned. So, when it comes to y n h, okay, so let me summarize how I have chosen y n h. To minimize y of h plus y n h for a given y of h, what one should do is the angle of y n h should be phi m. Okay. Then the magnitude of y n h should be such that y of h plus y n h is perpendicular to the boundary. So, perpendicular to the boundary means which boundary? There are two boundaries. One which corresponds to the angle of the admittance being equal to phi m. So, the boundary at which You are answering the other question, okay. So, the boundary at which angle of y and h is phi m. So, that is how we chose y and h. So, we still maintain this method of choosing y and h, but how to choose y of h is the question now. Again, we have the objective here. The objective is to maximize y of h plus y and h. Yeah, any answer? How to choose y of h? Now, first I have to choose y of h, from then I can show y and h. Once I know y of h, then I know how to choose y and h. That is what we discussed just now. But the question is how to choose y of h in order to satisfy this objective, maximize the magnitude of y of h plus y and h. See, one point to notice, this complex number y of h plus y and h is always perpendicular to the boundary, is always perpendicular to the boundary. Now, as the boundary goes further from the origin, we get a higher value of the absolute value y of h plus y and h. So, what is the maximum distance to which the boundary can move, so that I get a maximum value of this magnitude y of h plus y and h. Yeah, when the boundary is tangent to the semicircle. Is that clear? Is that obvious or not? Simple, I mean, simple geometry, nothing more than that. So, once the rule is fixed for choosing y and h, it should be always the sum of these two complex numbers y of h plus y and h should be always perpendicular to the boundary. So, I have to choose the position of the boundary itself such that it this perpendicular distance is maximized. Okay. So, that means I have to choose the boundary choose the boundary as a tangent to the semicircle. So, of course, there are many tangents, which say tangents can be taken anywhere. So, which tangent has to be taken? Huh? Y of h makes a, yes. So, the boundary should make an angle phi m with respect to the g of x. Okay. So, if I extend this tangent, so it intersects g f and it makes an angle. Okay, let me show this. So, first I should take the tangent. So, the tangent should be the one which is chosen like this. So, what is this angle? Phi m. This is phi m. See, the idea is very clear here. If I take this angle, this is phi m, so this is also phi m. Okay. Yeah, I have chosen the tangent. Now, where is y of h? It is a point common to the semicircle and the tangent. Okay. So, what I used red, red. So, I will show y of h. So, this is y of h. Then getting y of h plus y n h is very simple. Drop a perpendicular from the origin to this boundary. So I have used what color? Okay, blue. So just drop a perpendicular. So this will give y of h plus y n h. So once I know y of h plus y n h and also y of h, I can find easily what is y n h. So this is the worst case value, okay, of y n h that I am taking, green. Okay. So this is y n h. Now, please note, just by choosing y of h will not give me the values of the parameters of the filter. There are 3 parameters of the filter, R, L and C. Okay. Y of h will give me only 2 parameters. So, essentially I am not getting the parameters of the filter. See, y of h will give me what is GF and what is BF. It will not give me what is resistance, what is inductance, what is capacitance. It is still not giving me. Okay. So, see, please note, even if you take impedance, if I know the resistance and the effective reactance, it does not mean I know what is L and what is C. I just know what is X, which is omega L minus 1 by omega C, that is all. I still do not know what is L, what is C. Now, there are infinite values of L and C which can be chosen to get a effective X for a given value of effective X. So, the same thing is here. So, just by knowing the value of y of h, I do not have the parameter values. So, how to get the parameter values? So far we considered performance. So, these are the things which have to be done in order to meet the performance or maximize the performance. Now, we will see how to actually do further design. I mean, we have not completed the design. See, design is completed only when we have the value of RLC. Okay. So, for that we will minimize the cost and get the values of RL and C, minimum cost filter. Now, when it comes to the filter, what are the frequencies that will flow through the filter? What is the frequency of the currents that will flow through the filter? It is designed for a particular harmonic frequency, IH will flow, then any other current will flow. Actually, it is not IH, please note, we have used a different notation. Yeah, one has to be careful while, see, if you look at this figure, the current through the filter is not IH, the current through the converter is IH, the current through the filter is IFH. Okay. So, the two are not same. Okay. IFH is a current which will flow through the filter. Any other current, any other harmonic current will flow. Please note, it may not offer infinite impedance to other frequency, though it is very large impedance to other frequencies, it is not infinite, so it may flow. So, what about fundamental? It will not offer even infinite impedance to fundamental frequency also, but in practice what happens is, the harmonic current for which it is designed will flow. In addition to that, the fundamental will be significant, whereas the other harmonics for which it is not designed, I mean, there the magnitude of the current will be negligible. So then the significant components of the current that will flow through a filter are the harmonic frequency current for which it is designed and the fundamental. The remaining harmonics, I mean, the filter will offer a very large impedance, so it's insignificant. So we will make an assumption that only fundamental component. So I will use a notation IF1, F for filter, 1 for fundamental. Please note, this fundamental component is not the fundamental component of current through the converter. This is the current through the filter. Only the fundamental component IF1 and harmonic component IFH. Of the current are assumed to flow through the filter. Now, when it comes to cost is dependent on what? If you take any electrical equipment, can I say the cost is almost proportional to one particular rating of that equipment? What rating? Let me take for example transformer. If I say the cost is proportional to some rating of the transformer, what rating? Voltage rating? Current rating? It is volt ampere rating. It's actually volt ampere rating. Now, when it comes to filter, what rating? Again, so filter is an electrical equipment, it's again the volt ampere rating. Now, when you if you see the filter, it's essentially L and C. R is something which comes for some reason. So, R is not a very significant part of the filter. So, it's only L and C. When it has only L and C, there is only reactive power. So, it is proportional to the reactive power rating. The cost of the filter is proportional to the reactive power rating. So, what is the reactive power rating? So, there is an inductor, there is a capacitor. So, let us try to take the reactive power rating of the inductor and capacitor separately. The reactive power rating of inductor. So, I will use a notation for this QL, L for inductor. Okay. So, can I get an expression for the reactive power rating? See, we have made some assumptions that we are neglecting the other harmonic components. So, only IF1 and IFH flows. Okay. So, there is only the fundamental current and the harmonic current for which the filter is designed. So, based on this, can we get an expression for the reactive power? Now, please note, reactive power is something which is difficult to define in the presence of. See, reactive power has a well-known definition in the present, when there is only fundamental component. Of course, there have been attempts to generalize the definition of reactive power in machine theory. They use, the Pacron's transformation can be used. But when it comes to steady state, there are attempts to give other definitions. One particular definition is the one given by a person called Budanu. I don't know if you have studied power quality. You may, how many of you studied power quality? Have you heard of this Budanu's definition of reactive power? There are many other definitions. Budanu is one particular. So, there are many ways in which we can define reactive power. So, one of them is Budanu's definition. So, what is the reactive power according to Budanu in this case? What is that particular definition? You take each frequency, find the reactive power and add them, that you say that is the total reactive power. That is what is Bodanov's definition. Okay. So, if I take only the fundamental and harmonic, there are only two when it comes to filter. There is only the fundamental and harmonic. There are only two frequencies. So, find the reactive power for fundamental, find the reactive power for the harmonic frequency and add them. So, what is the reactive power corresponding to fundamental? See, the current is IF1. So, how do I get reactive power from current? No, it's not necessary to get into complex. IF, yeah, IF1 square into reactance. The square of the current into reactance gives reactive power, right? Okay. So, what is the reactance? Now, please note we are calculating the reactance. Reactance depends on frequency. So, we are calculating at fundamental. So, what is the fundamental reactance? In terms of the quantities that we have used, L is the inductance. Okay, there is inductance L. What is the fundamental angular frequency? We have not used any specific value of frequency. Using the notations that we have used, notations omega h star divided by, see, omega h star is the harmonic frequency for which the filter is designed, divided by h gives the fundamental. Is that okay? Is that okay? Plus, now please note I am just taking the ideal value of omega h. So, ideal value is omega h star. So, in practice omega h will deviate. So, because of that the reactive power rating will slightly be within a band. So, I am trying to take the ideal value of the frequency and compute the reactive power. Then if I take the harmonic frequency, it is IFH squared into reactance. So, in this case it is omega h star into L. Okay. Now, this can be written as IF1 square by h. Omega h star is 1 by root LC. It is 1 by root LC. Omega h star is 1 by root LC. So, please note omega h star is 1 by root LC. So, using this I can write this as root L by C, the first term. Similarly, the second term is IFH square into root L by C. Okay. Go back to, so we are doing a very simple design. This is a very simple design where we are ignoring the effect of change variation in the inductance and capacitance. We are taking only one. So, if you consider that, it will become even more complicated. Okay. So, similarly, I can define the reactive power rating of capacitor. So, reactive power rating of capacitor. QC is a notation for it. So, again I can use the Bodanov definition of reactive power and write the reactive power rating as sum of two reactive powers, one for fundamental, one for harmonic. So, I will stop here, continue from this point in the next class, then complete the design.